Let's consider what would happen if we were to take water and heat it up from minus 25 degrees Celsius all the way to 125 degrees Celsius. Now, lots of things are going to happen there. You're going to get an increase in kinetic energy, and in some cases that increase will lead to, well, increased movement of molecules, and therefore an increase in temperature. And then that energy, the kinetic energy, goes into a phase change. Changing, in this case, you can see here's where melting would take place as we heat things up, and then you'd heat up temperature again, and then another phase change. So to go through and calculate the amount of energy it would take to take water from minus 125 degrees all the way to minus 25 degrees Celsius all the way to 125 degrees Celsius, we would have to consider that there's going to be different phases involved and different phase changes involved. And it's best represented by looking at something called a heating curve. A heating curve plots the temperature as a function of the heat that is either absorbed or given off, depending on which way we look at the curve. And so from that, you can use this as a way to calculate the energy that's needed. And so in order to do that, we will find out that here's one phase where the temperature is changing from minus 25 and it warms up to 0. And so the heat in this case is being absorbed and is completely being used to change temperature up until that ice, because this is all solid, begins to melt. Then all the energy goes into the melting process. Once all that ice is melted, then it again goes into a temperature change process as you go from 0. So now this is all liquid. So the liquid starts heating up, and in the case of the liquid, all of the heat is being transferred into molecular motion of the molecules, which increases the temperature. And then you hit the temperature at which boiling occurs, and then all of the heat, instead of going into continuing the increased temperature of the water, goes actually into turning that water into vapor. And so you start seeing it, the phase change, all the heat is going into the phase change, and then starts over again. Now the gas is starting to heat up to 125 degrees. So to go from minus 25 degrees all the way to 125 degrees, you have to kind of see that there's going to be 5 different areas that we need to consider in order to calculate that energy. Now, if we assume that we're heating up 1 mole of ice, starting at 1 mole of ice, heat that up to 125 degrees, so we'll wind up with 1 mole of gas, what we would find out is that the energy in this 1 mole to heat it from minus 25 all the way up to 0 is going to be, if we calculate it, will be 0.941 kilojoules per mole. So in other words, 1 mole of ice, 0.941 kilojoules. Okay, that's how much energy it would take just to heat 1 mole of ice up from minus 25 to 0. Then to melt 1 mole of ice, we will see that that will take 6.02 kilojoules to melt that 1 mole of ice. Then to heat the liquid water, the 1 mole of liquid water, to heat it from 0 to boiling would take 6.52 kilojoules per mole. So we'll see that that takes 7.52 kilojoules. So this will take 7.52 kilojoules. Then to boil that much 1 mole of water, it would take 40.7 kilojoules. to boil 1 mole of water. And then to heat up the water vapor from 100 to 125, so to go up an additional 25 degrees, would take 0.904 kilojoules to make that happen. And then if you want to know the total amount, you would add these together, and we would be able to learn that it would take, I always forget that it would take 56.1 kilojoules to heat 1 mole water, or ice, or whatever you want to say, from minus 25 degrees to 125 degrees Celsius. So this is degrees Celsius. So that's what it would take. So how did they get these numbers? How is it that we could calculate that this part, we can figure out how much energy it takes to warm this up, to melt this, to warm this up, to evaporate this or boil this, and to warm that up again? Well, we treat each segment separately. So let's see how that's done. So for the first part, I'm going to draw this out here a little bit. So for the first part, we go from, here's 0 degrees Celsius to minus 25 degrees Celsius. So for the first part, we want to know how long does it, not how long, how much, Q means heat, by the way, how much heat does it take to warm up water, 1 mole of water, 25 degrees? And so we use this equation to figure that out. And you've used this in your past experiences in Gen Chem 1 when you were using calorimetry. You may not remember it, but you did. So you take the mass of your water, and since we know we have 1 mole of water, we know that by molecular weight, that's about 18 grams, 18.0 grams. So we can just use 18 grams of water. So that's what we put in for mass. And then we need to know what the CS is. Now, CS, that's the specific heat capacity. So that tells you how much heat water can absorb per gram. And you can see that actually, if you look carefully, you can see joules per gram per degree Celsius. So this tells you how many grams, how much heat it would take per gram to raise the temperature 1 degree Celsius. That's what this tells you. And notice that this is in joules. And so one of the things we'll show you is you got to pay attention. Is it in joules or kilojoules? So the enthalpies tend to be listed in kilojoules, where the specific heat capacities are listed in joules. So you just have to make sure that when you do your calculation, you account for that. And then delta T, just as a reminder from the olden days, is equal to the final temperature minus the initial temperature. So our final temperature in this case is 0 degrees because we're warming it up to 0. And then from that we will subtract the initial temperature, which in this case is minus 25. So if we plug all this in, you'll get 941 joules, or 0.941 kilojoules. And you just need to decide for yourself if you're going to come up with your answer always in kilojoules or joules. You'll have to pay attention to that. Now let's look at phase 2. I should say segment 2. Phase, when we're dealing with this kind of stuff, I should probably be more careful. So let's do that. All right, segment 2 and segment 3. So we'll be able to build off of that. So I'm going to go ahead and again, I'm going to leave this like this. You should be able to see that. And again, I think it's helpful to sketch our heating curve. So again, Q means heat, temperature. We did segment 1 already, and we found that it had 0.941 kilojoules. It took, I gotta erase this mess I just did, 1 kilojoules. And that's 0 degrees Celsius. Here's minus 25 degrees Celsius. Okay, segment 2 is melting. And we want to figure out, how do you melt 1 mole? Well, here we go. You use this relationship. The heat it takes to melt 1 mole is going to be calculated this way. So N is the number of moles, and since we have 1 mole of ice, we're good to go. And delta H of fusion, and fusion is just another word for melting, okay? And freezing, you can look at that. So delta H of fusion is 6.02 kilojoules per mole. So we plug that in, and we can calculate that segment 2, since there is 1 mole, is 6.02 kilojoules, because the moles cancel out, right? Now, segment 3. We need to take that 1 mole of water and crank it up to 100 degrees Celsius. Well, we use this same equation again, where again, just to remind you, delta T is the final temperature minus the initial. All right, and the specific heat capacity for liquid water, sorry, this is wrong, is 4.18 joules per gram per degree Celsius. Now, these are things you look up in a table, or you get them provided for you. You know, if something like this was on a test, you would never be expected to memorize all these things. You'd be given them. So the specific heat capacity for water, which is going to be different than that for ice or gas, is 4.18. And this, I didn't catch this error before, cut and paste error, but I caught it now. So you know that 1 mole, just like we said before, of water is 18 grams, and you plug it in. Here's our final temperature. Here's our initial temperature. And when we do all the math, we either have 7,520 joules, or 7.52 times 10 to the third joules, or 7.52 kilojoules. So this heating is 7.52 kilojoules. All right, then we got to do the next segment. And so for segment 4, again, I'm just going to continue to build on this. For segment 4, okay, we have segment 1, segment 2, segment 3. Segment 4 is boiling. And so this was 0.941. This was 6.02 kilojoules. This segment 3 was 7.52 kilojoules. Now we have to figure out what it is for 4. And since this is boiling, we use a very similar, for phase changes, you're going to use a similar equation. You'll use the heat is equal to N, which is number of moles, times the appropriate enthalpy. In the case of boiling, it's enthalpy of vaporization. Okay, so we know we have 1 mole of ice, because that's what this is. So now you have 40.7 kilojoules of ice, because 40.7 is the enthalpy of vaporization. And so we can write that in, 40.7 kilojoules. And then it goes up to, so this is, I'll write this up. This is 100, 0, minus 25.0, and then 125. So we got our last segment, which is a change again. Again, delta T is the final minus the initial temperature. So our final temperature here, our initial temperature is here. Here's our specific heat capacity for water gas, 2.01, and then 18. So if we punch that in, we get 0.904 kilojoules. And then to get the final number, we add them together. And as I mentioned that, as I did the math before, it comes out to 56.1 kilojoules. So that's the overall approach that you take. So let's just kind of map out sort of a strategy. Okay? I want you to try this. I want us to use water again, but let's do a different problem together. So let's say we want to figure out how much energy. So I want to figure out what is the energy, the heat involved in lowering the temperature of water from, we'll say, 105 degrees Celsius to minus 8.00 degrees Celsius. So how much energy is involved in lowering the temperature of water from 105 degrees Celsius to 8 degrees Celsius? And let's say that we're actually using this on 100.0 grams of water. So we want to figure that out. How much heat is involved in lowering the temperature of water, 100 grams, from 105 to minus 8 degrees Celsius? So I find that it's really useful to be able to sketch this out so you can kind of see it. Okay? So sketch it out. In this case, we're going from 108 degrees. That's our starting amount. So we're going to be cooling, right? And we're moving it all the way down to minus 8. Sorry, 105 to minus 8 degrees. Okay? So we're moving from 105 degrees to minus 8. So what I do is I map it out just like you see. Then I'll write in what the phase change temperatures are going to be. The boiling point is 100 degrees. We know that for water. Now, I wouldn't expect you to memorize that for all materials. You'll always be provided that kind of information for calculations and stuff of this nature. And then we got 0. Now, I didn't draw this to scale. I just drew this so that I could easily map it out. Okay, so we have temperature, and we have so first thing I do is I'll assign my phases. And even though we're cooling, I still write it out the same way. I know that I'm going to get some kind of warming up. I'm going to get some kind of phase change, either melting or freezing, I'm either going to warm it up or cool it. I'm either going to warm up the water or cool it. I'm either going to boil it or condense the water, and I'm even either going to heat or cool it. So I have, in this case, since I'm dealing with all of this 2 phase changes, I'm going to have 5 sections, and I'll just name them like this. Okay, now let's write down some stuff. All right, we know we have 100 grams of water, so divide that by 18 to get the moles of water. So I think it's useful to just calculate and find all the information you need. So the rest is just plugging in the values. So 100 grams of water is 5.56. Well, actually, if I use 18.01 for my molar mass, I would say 5.556 moles of water. So I got 5.556 moles of water. And so I got those 2 things. Now I also need to look up, and since we just use them all, I can remember we need to know the heat capacities of, I'll just put L for liquid, heat capacity for gas water, and heat capacity for ice. I'll just say solid. And then we need to know delta H vap and delta H fusion. Okay, so we got all these things. Let's write them out right now. You can look at your notes. You just use them. So I wrote them all in, and you could look those up as well. But here they are. We know that we have for our specific heat for liquid water, 4.18 joule per gram per degree Celsius. For gas, steam, 2.01 joule per gram per degree Celsius, 2.09 joule per gram per degree Celsius. And so the delta H vap, 40.7 kilojoules per mole, and the delta H fusion is 6.02 kilojoules per mole. So we need to take all this into account to come up with our changes. Okay. Now here's the thing. In the first case, we're talking about heating the water. In this case, we're talking about cooling it. So we're going from top to bottom. And if you think about it, that means we're going from right to left when it comes to cooling. We're removing heat. Heat is leaving. And when heat is given off, it should have a negative sign because heat is released. So it turns out to go from 105 to -8 turns out to be exothermic. And to go the other direction, if I wanted to go from -8 to 105, that would be endothermic because heat would be involved, absorbed in order to do that. So now what I need to do is write out each of these segments just like we did earlier and plug in the numbers and do the math. So I'm going to actually write out each segment, but I am not going to necessarily solve every step. I'm just going to give you a sense of what we need to be doing. So we can start off then, and it doesn't matter how you do it. I'm just going to, even though we're starting at 105, I can write my segments any way I want as long as I just pay attention to which direction they're going to go. So in segment 1, I'm just saying that is the cooling of water from 0 to -8. And I know that I have, so I know that I want Q, and Q is going to be 100 grams of ice being cooled, because 100 grams of gas, steam, you know, however you want to think about it, I'm using 100 grams of water. That doesn't change. And then I need to pick the correct phase, and so the solid phase is what I want there. So I'm going to multiply it by the heat capacity, 2.09. That's joules per degree Celsius per gram. And I'm going to put my final temperature, which is -8 minus 0. And then you'll calculate, you'll get whatever you get. Then you do this. And it should be a negative number. Now, I'm going to look at this phase change. Before we looked at melting, now let's look at freezing. And even though we're freezing, we're still going to use delta H fusion, but here's where the difference is. We're going to take delta H fusion, and we know we are going to use, let's see here, we got 5.556 moles of water. And now, because we are dealing with freezing, instead of using positive delta H of fusion, we use a negative delta H of fusion. And that's kilojoules per mole. So remember, if you do this first one as I have here, you'll calculate it in joules, and then you'll convert that to kilojoules. Or if you do this one, you're going to get kilojoules and convert to joules. It depends. You just have to keep the same values. So if I do number 3, segment 3, we are doing a temperature change again. So temperature change. And this time we're dealing with water's temperature change. So I know I have 100 grams of water. And I know I have 4.18 grams, joules, sorry, per gram per degree Celsius. And I know I'm going from, my final temperature is 0.00 degrees Celsius, because that's what I'm going to end up at because I'm cooling, but I'm starting at 100 degrees Celsius. And I'll just put in the extra 0 there. I think that's fine. All right. Then we'll move it up, and we can continue on. And now for this part, we're dealing with boiling, and in this case not boiling but condensing, because we're taking the gas and condensing it into a liquid. So I can just go ahead, I can calculate my heat again, and this time I need my delta H vap, and so I know I have 5.556 moles. And again, because now I'm condensing, I take my delta H vap and I put a negative sign, because that's heat that will be released as we go from gas to liquid, and that's kilojoules per mole. So that should be a negative number again. And finally, we have our heat and another temperature change. And in this case, the temperature change deals with the gas. Okay? So in that case, I can just go ahead. I know we have 100 grams of the gas times 2.01 joules per gram per degree Celsius. And my final temperature in this case is 100 degrees, and from it I subtract 125, no, 108, no, 105. Boy, I got problems, I tell you. Okay. I'll just leave those in there. It should be. Anyway, so that's what we got. And so now you can calculate all that, add it together, and the amount of heat that's involved should be, drum roll, minus 304 kilojoules. And if you didn't get that answer, you may want to visit the CIC and see if you can come up with it. And remember, it makes sense because it's negative, because negative, first of all, if you do this, it will be negative, but you expect it to be negative because you're starting at a warmer temperature and moving down to a cooler temperature, and that should yield a negative sign for heat, indicating that it's released, which makes sense. You're cooling it. Alrighty, let's talk about phase diagrams. So, last part of this chapter, well, of this discussion, I should say. Let's talk about phase diagrams. Now, phase diagrams are a way to look at materials. You'll see phase diagrams used in different disciplines, not just chemistry. I've seen them personally when I've been to talks dealing with geosciences, so geology and that kind of thing. Plus, a lot of materials deal with that too, so like material science. So phase diagrams, I'm guessing for some of you, you've seen these before. And they have different types and different meanings, and different things are plotted. But the general idea is you take a set of conditions and you plot one of those against another. In the conventional one, the one that we're going to do for this in Chem 112, is we're going to plot pressure versus temperature. And the way they all will be pretty much is you will see that essentially depends on the material. Water looks a little bit like this, where you can draw a Y, and each of the lines here represents a phase boundary. So, and I'll talk about that, but when you have different pressures versus temperature, different pressure versus temperature, you'll get different phases. So in the leftmost phase is going to be your solid. And then the one that's kind of in the Y, up in the, where the branch point is the liquid. So that's your liquid. And gas is the last one, okay? So each of the lines then represents a phase change at the different pressures, okay? So this here would be melting, and this would be freezing. I'll just abbreviate that. Of course, that's boiling. We go from liquid to gas, and that's condensation. And then going straight from solid to gas is called sublimation. And to go from gas straight to solid is called deposition. So those are the different phase changes that can happen, and each of the borders between them represents the pressure and temperature for each of the phase. So this line represents the temperature and pressure kind of arrangements where you would have melting. Here's your temperature pressure arrangements where you have boiling. Here's your temperature pressure where you have sublimation or deposition. So that's kind of the general idea. And then, furthermore, we can look at certain points. And I'll draw this point here. That blue has, that's called the triple point. And the triple point is where a solid, a liquid, and gas all coexist. All three major phases coexist. And then right here, that point there is called the critical point. And above that temperature and pressure, we have something called a supercritical fluid. And the supercritical fluid has unique properties. So this phase has properties of a fluid. It has some properties of gases, some properties of liquids. And one of the things it's super duper good at, it's a good solvent, it turns out. They're really good at dissolving things, supercritical fluids. And a great example of that is, for some people, an abomination, is decaffeination of coffee. So supercritical carbon dioxide, so that's carbon dioxide that's above the critical point, so it has high enough pressure and temperature where you get a supercritical fluid, and that's used to decaffeinate coffee. So you can put the actual green coffee beans into caffeinate, I think that's right. Those might be switched around, I don't know. Anyway, you can use it to decaffeinate coffee beans. So you take the green beans and you put them into a chamber where you can create the pressure, temperature needed to have supercritical CO2. And when that happens, that liquid can go right into the bean and it dissolves out the caffeine and you can extract it right from the bean. And then that bean no longer has caffeine, and the supercritical fluid, once you remove it and then let it come to room temperature, all you have left is pure caffeine. So you can actually purify the caffeine that way. So that's about the phase diagram. So if you change the pressure and you change the temperature, you can change the phase. That's why sometimes you can actually cause things to boil at a lower temperature than normally, than at the normal boiling point. So if I were to draw this line right here, and I say that's the line at 1 atmosphere, whoops, if I call that the line at 1 atmosphere, then that's your normal melting point, and that's your normal boiling point. And we talked about normal boiling points. Okay, so that's the temperature at which boiling takes place at 1 atmosphere, or 760 torr. So you can use that information. So anyway, so that's what we'll find. So I like to get students to think about things, and so you can use a phase diagram to describe why ice skates work. And you can use this phase diagram for that, because if you think about it, here you got your ice, and you got your, now I am drawing this is an ice skate coming at you. So there's the laces, and it's coming at you. So the human or the person skating, all of their weight is focused on this little tiny blade, and that creates an enormous amount of pressure. And so by increasing the pressure to a high level, in the case of water, water's unusual this way because water has a weird, I drew a phase diagram similar to water, and so the water has an unusual case where the phase diagram goes like this. So as I increase the pressure, look what happens to the freezing point. it decreases because it goes that way. So you get a layer of slippery water underneath your skate. Now, if you made it cold enough, and in Wisconsin, I've seen it cold enough, you can make it so ice skates don't really slide at all. Ice isn't slippery at cold enough temperatures because it stays ice. You don't get that little layer of water that can be forced just by having pressure pushing down on it. That's what this phase diagram tells us. Most other materials will have something a little bit more like this for their shape of their phase diagram. Okay, so you don't see the back slant that you see for water. They usually slant a little bit forward, but different materials have different properties. And then if you've seen phase diagrams like in materials, you know that even within just the solids, there's different types of phases that show up. If you're dealing with rocks, which is also solids, you may get different types of phases depending on pressure and temperature or whatever the two properties are that you're doing. So that's get some practice working with phase diagrams, be able to draw one, be able to label them, and explain where melting and freezing happens, and boiling and condensation and all that kind of thing. You know, maybe think about this example that I just gave you. Be able to explain why ice skate sometimes works great and at cold enough temperatures does not, and be able to use the phase diagram of water to do so.